Can a single point in space really change the entire energy structure of a quantum system? Find out as we inspect the infinite cubical well step by step using degenerate perturbation theory. The question today poses that we suppose we perturb the infinite cubical well by putting a delta function bump at the point given, such that the Hamiltonian now takes the form of a cubed v naught delta 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 for all three dimensions. And from this, we want to find the first order corrections to the energy of the ground state. Remember, cubical well ground state has n equal 1. And the triply degenerate first excited states. Cool. If you don't remember this, we actually found these degeneracies in problem 4.2. So hang on to that thought as we move through. But why do we care? Well, not every quantum system is nice behaved and has non-degenerate energy values or energy spectra. So we have to be able to deal with these energy spectrums and to the lifting scheme that perturbation theory provides us. That being said, we know that the first excited state has a triply degenerate spectra. So how many matrix elements would the second excited state have? Now, keep this in mind as you see as we get through this question, why more degenerate states lead to messier and messier calculations, and then we'll start to see why computer programming starts to save the day when it comes to these ridiculous amount of calculations. That being said, because this does have a lot of steps in it and is going to get very messy, please don't forget about the PDF because you're definitely going to want to get a copy of it to hold for your notes. You can access that using the link below, the free companions. We've seen that for a couple chapters now, so please make it available to yourselves. And if you find value in this content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. No account required. Now on to the fun. Alright, so stop number one then. We first have to get a grapple on what's going on in all these sectors. Because the ground state, or n equal 1, is non-degenerate, we can use equation 7.9, which is just the expectation value of the new Hamiltonian. Okay? So with that, or the perturbed Hamiltonian, excuse me. So with that, what we see here is that in order to understand what states we have for the three-dimensional well, we have to go back and adopt the notation, okay? And that was nx, ny, and nz because we could alter those principal quantum numbers in each dimension, and that gave a new energy spectrum. But for the ground state, we saw that all three of them had to equal 1 to get to the lowest state. So thankfully, we have a pretty easy inner product to deal with. And again, in the PDF, I break this down into all the definitions, all the boundaries on the integrals, etc., etc. But for the sake of conciseness, I think we can see how one thing translates to the next here. So, that being said, our wave function was given to us in the form from equation 2.31, and we just extend it out to 3 dimensions. So pay attention here that this first one that has x takes the first number here, the y second, z third. That will come into play much later, but you want to see it now. That being said, we see that these are all the wave functions, and because it's all real, we don't have to worry about the complex conjugate, so we can smush them together in this square. But we also note that here, the perturbed Hamiltonian brings us to a cubed v naught with all three deltas. Thankfully, the fact that this is a delta potential saves us multiple headaches in the integration, because we can just use the shifting property and clear out the integral. Take note that there's 3 square root of 2 over a for the length of the cube in each direction. So with that, we can take all these constants out front and simplify. So since we had 3 copies and they were all squared, we just got 2 to the 3 over a to the 3. Cool, we brought out the perturbed Hamiltonian a cubed v naught, and we see that those cancel. Lovely. Next, we see that because we had 2 similar states, every function in it got squared. Wonderful, wonderful, wonderful. Reason now, we plug in the shifted value from the delta, and we realize that the length of the sides, clearly they all cancel, so it doesn't matter what length of the well is, we can cancel out everything perfectly. And because all states start with a 1, so nx equal 1, and y equal 1 and z equal 1, we just get sine of some easy values to calculate. That being said, sine squared of pi over 4 is just the square root of 2 over 2, or if you're just in the physics mindset, 1 over root 2 works just as well, but you still have to square that. Then you have a 1 here from pi over 2, and then 3 pi over 4 is still a plus. For some reason, I thought that was a negative. I'm thinking it's in the third or fourth quadrant, but nonetheless, we're good there. So with that, we see that we get 1/2 here, or 2 over 4. 2 over 4, that combines to 4 over 16, which gives us a 1/4. So 8 divided by 4 gives us 2. And that is the first order energy correction for the ground state in this cubical well. So now that we're done with that, we have to start setting the stage for stop number 2, which is for the first excited state, or the n equal 2. Now, we have to be careful here because this n represents that everything is in the second energy level. Now, we can obtain that from 3 different characteristic combinations. Okay, so if we were to go back to the picture of ny or nx, ny, and z, and set one of them equal to 1, 1, and 2. We could also shuffle that to 1, 2, 1, and 2, 1, 1, and get the same energy level, but different orientations. So that was what we saw from problem 4.2, and we resolved that fairly quickly. You just have to really be careful in setting this up. And setting up for the degenerate perturbation theory, we have what's called the W matrix, and that takes into account all the different mixture of states. So instead of having nx, ny, and nz on both sides, we have the primes on this side. Doesn't really matter which side you prime, but in this specific setup, instead of there is a shortcut that I walked through in the PDF, but because of the delta functions, we can simplify this calculation pretty quick. And again, because everything's real, we don't have to worry about complex conjugates or transposes in this case because it's a function, not a vector. We're good there. The 8 times v0 comes from this simplification here. So we're good there. And we really just have this product of 6 sine functions. Okay. And that was all thanks to equation 7.40 for these matrix elements. Now, if you want the full gory detail, please reference the PDF again because it definitely is a lot of work and it's much easier to set up this general form now instead of having to pump out 3 integrals every time, because as you see we have 3 different degrees of freedom here that can be modified, and in a square matrix that leads to 9 elements. So think about that for the challenge question of, well, if I go to another higher degeneracy, how many states am I going to have? It definitely will make a difference. Again, the first excited state saves us a lot of trouble, and we're going to, in the book, they label these as matrix elements AB, and A will just be the one. Let me just write that down here too. For A, we will just use the combination where we're 1, 1, 2. For state B will be 1, 2, 1, and state C will be 2, 1, 1. So when you look at the indices here, these are the numbers we're representing here, and I'll try to color code that as best as possible. But again, the PDF will have all that nice detail for you. But nonetheless, let's push forward. Okay, so as promised, we're going to use the book notation of state A and state A mixing. So we see that we have 1, 1, 2, 1, 1, 2. Again, this is the ground state wave function though, so we're good there. We don't have to worry about any modifications to that. Now, moving forward though, you see why we just want to get a general form for what this is, because then we can plug in nx, ny, and z, nx prime, nxy, and xz. And we see that that delta function really just saves us a lot of headache. Okay, so here, then we just see the values of the signs all multiplying one another. Clearly, negative, negative cancel. And we get to push through to a 8 v0 times 1/2 after simplification to a 4 v0. That's nice. We really like it, but that's only one of 9 components. So let's wrench through the rest And we see that we have mixed state AB, so 1, 1, 2 and 1, 2, 1, color coded to try to match that for you. And we see that just evaluating these, we love zeros, makes our life easy. So 0 times all that leads to a 0, and we're good to go. All right, our final mixed state in the AC configuration, or the A leading configuration, 1, 1, 2, 2, 1, 1, simplify down, we get a negative 4V0. Now, this is our next main diagonal term right in the middle, and as you see, B and B, we get 1, 2, 1, 1, 2, 1. Evaluate the signs accordingly, and 2 0 terms pop up. We love zeros, simplifies nice. Now we're on to the first mixed state with B leading, so 1, 2, 1, 1, 1, 2. Oh, look, we get 0. That was the same value as WAB from the last slide, so keep that in mind whenever we go to construct this, because there is a clever trick that can be utilized here to save you time, and you could thank the linearity and the symmetrization of the W matrix for this, but very clever, and you'll see in due time. All right, so now on to the other mixed state with B leading, which is B and C. We have 1, 2, 1, 2, 1, 1. Simplify down. Oop, another 0. Gotta love it. Finally, our last main diagonal term, so WCC. We get 2, 1, 1, 2, 1, 1. So put them all together. Good to go there. We get this times 1/2 again, so we get a 4V0. Awesome. Now our first mixed state with C leading, we get a 2, 1, 1 because of the C, and A is 1, 1, 2. Put that together, you get a negative 1/2, so you get a negative 4V0. But this was also the value that we saw with WAC. So we're looking a little bit like a symmetric matrix here. And our final mixed state with CB, where we have 2, 1, 1 and 1, 2, 1. Put them all together, you get A, and then you get a 0. Cool, we like zeros. And so this is the general form of the W matrix. As you see, all indice pairs and mixed states come together. Wonderful, wonderful, wonderful. Here is the clever little trick that you can use, and I highly suggest you do so if you're writing it out by hand. Wij is equal to W conjugate Ji. Okay, now again, these are all supposed to be a single value, so we don't need to transpose it, so they're scalars. So that is the true complex conjugate of everything. And with that, all you really need is the main diagonal terms and an upper triangular set, So what that means is you really need to calculate these same states and then sum of either that upper triangle or this lower triangle, and that takes the calculation down from 9 elements into 6. So it definitely reduces computational time. And we see here that with all the entries plugged in, WAC, negative 4V0, same thing over here, complex conjugate, same value. We have, and then we have 0, 0, so we're good there. Again, we see that it is symmetric, i.e., if we take the main diagonal here, draw a line through it, and we transpose it, they're the same value, so we're good to go there. Clearly, this is much easier done when you factor out the common factor of 4V0, and then we'll multiply it in later after we find the eigenvalues. But be aware, there are definitely clever tricks that can be used, even though this is a fairly brute force kind of calculation problem. Those tricks will come into account when you need to calculate something that has, I don't know, a degeneracy of 6, because then you have 36 elements. That's a lot. We don't want to be doing 36 calculations. So any shortcuts you can make, definitely better off. That being said, hope you are a fan of linear algebra, because in order to find out what the energy values are and the corrections, we need to find the eigenvalues of this. So let's go ahead and dive into that. All right. Thankfully, we also know that the W matrix gave the matrix equation given by 7.41, and all we have to do, set up the characteristic equation for the eigenvalues. we see that the determinant here of W minus E1, the first order corrections, which are the eigenvalues, and if you want, you can label this as lambda. Same idea. Just make sure that your notation is on par and that you know that that's for the first order energy correction. All the gory detail again is brought up in the PDF, so just be aware it is a thing. Here we have 4v0 that was factored out, and if we're setting this determinant equal to 0, we can get rid of it as a common factor. All we have to do is be aware that we need to put it in later, as you kind of see down here. There are also several tricks in linear algebra in terms of finding out how to calculate the determinant. And generally, we saw that, especially from cross products, we had a plus, minus, plus, minus, plus, minus, plus, minus, plus in terms of the determinant entries. So if you were to use cofactor expansion, you could use the second row since it has two zeros in it, and then you would just be multiplying cross terms like this and this, so on and so forth. That is, in my estimation, a lot easier to deal with, so try that method out, and you see that you get this characteristic equation here. And all we have to do is solve for the roots, which are the eigenvalues, so that would be E1. So after simplifying this down, we see we have a common factor of E1 squared in both of these terms after full simplification, because that cancels with the linear factor here. You get a cubic factor with all three of these. So go check out the PDF for all the little nitty-gritty details, but after that's said and done, we see that we get E1 squared times E1 minus 2 equals 0, and that gives us two cases. So we have the case where E1 squared equals 0 and E1 minus 2 equals 0. Thus, we have E1 is 0 with a multiplicity of 2, so that takes care of two roots. So that's two of the possible three degeneracy energy state corrections, and E1 equals 2. But because we factored out that 4v0 earlier, we have to now put it in for the energy correction terms down here. Again, with the zeros, easy to handle. So the energy corrections are 0, 0, and 8v0, and that brings us to our conclusion for this, and we see that all of these correction terms for E1, the first order, but the second energy state, very important. And of course, we just have to add these together for the degenerate energy levels, and we can see that that's what we're going to end up dealing with the total energy. So yeah, a tiny bump can lead to a massive difference, and that is going to be hectic when you're trying to get anything done in a lab, because let's face it, nothing's perfect. All right, so in summary, you saw how to deal with the higher order degenerate perturbation theory with the nice example. And I'm saying nice because that delta function is the only reason why we didn't have to spend 40 minutes on this video. So be aware, those delta functions are key to your physics understanding later. Green's functions keep coming to mind. I can never get rid of them now. But that being said, all this work is thanks to the supporters of this channel. So I must give a massive thank you to all of them for making this possible, because it definitely takes up a lot of time and energy. And of course, with that, I'm extremely grateful for all your support. If you'd like to see more, you can also become a patron for access to supplemental material, current and future projects, and one-on-one help. Especially now that the fall semester is coming in, people are finishing up their summer courses. I know a lot of people are getting ready to present on their thesis, so best of luck to you all who's reached out. And of course, new content is posted weekly, probably more daily soon, to fuel your curiosity. Again, once you get on a roll with this stuff, it's hard to stop. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.